In this video, I will discuss about the common emitter connection mode of the transistor. In the previous video, I have discussed about the common base mode connection of the transistor. Here, we will discuss CE mode connection of the transistor. In CE mode, the input is applied between base and emitter, and output is taken from collector and emitter. And here emitter terminal is going to be common for both input and output. That is the reason why this particular arrangement or this particular correct connection is called as common emitter connection. Okay. So this is the simple circuit showing the common emitter mode connection of the transistor. Clearly you can see in this NPN transistor, this is emitter, and this emitter is common for both input and output. Okay, emitter is common for both input and output. Here in input circuit, base is connected, and in the output circuit, the collector is connected with emitter as a common terminal. Okay, so this is NPN transistor, and for proper working of the transistor, emitter base junction needs to be forward biased and collector base junction needs to be reverse biased. And collector is N type, so that base, which is P type, should be connected to positive of the battery so that base emitter junction becomes forward biased. So VBB is connected so that base emitter junction is forward biased. Another battery VCC is connected in the circuit in order to make the collector base junction reverse biased. Here collector is N type. So N type semiconductor in the transistor is connected to the positive, means collector terminal is reverse biased. Okay. And one extra resistance is connected to the collector, which is called as collector resistance RC, across which the output can be taken. Okay. In order to understand the circuit behavior, first we will try to identify what are the input parameters here and what are the output parameters. So parameters are voltages and currents. So in the input circuit here, the current IB is flowing in the input circuit. Therefore, the input current is IB. And input terminals are base and emitter. So that voltage between base and emitter is the input voltage. And we represent it by VBE. VBE stands for base and emitter voltage, or voltage between base and emitter. In the output circuit, we can clearly see the collector current IC is flowing. So collector current IC is flowing, and output terminals are collector and emitter terminals, so that the output voltage is VCE, and that is clearly taken across the resistance RC. Okay. So in order to understand the input and output characteristics, these input parameters and output parameters are required. So let us take the important characteristics of the common emitter connection. First one is the input voltage and input current at constant output voltage. So it is called as input characteristics. Okay, it is the relationship between input voltage and input current at constant output voltage. While studying the input parameters, output parameters should be kept constant. So in common emitter mode, the input current is base current IB and input voltage is VB, that is voltage between base and emitter, and the output voltage VC needs to be constant while studying the input parameters behavior. Therefore, the input characteristic is the curve between base current IB and base emitter voltage VB. It is the graph of So in order to study this input characteristics, we have to keep VC constant, say at 10 volt. Then base current IB should be noted for different values of VB. Then we have to plot the graph of VB along x-axis and IB along y-axis. Okay, and you can observe a forward biased diode characteristic like behavior. So for Vc equal to 1 volt, you will get more current for low voltage, and as Vc increases, it will shift towards the higher voltage region. So you'll get a parallel curves if you take different values of Vc. Okay. So here you can observe up to 0.6 or 0.7 volt, there is no current through the junction, or there is no voltage, sorry, your base current is zero. Then afterwards, the base current increases rapidly. Okay, it is exactly similar to the diode characteristics when it is forward biased. Since it is the base emitter junction characteristic, so base emitter junction is always forward biased for proper working of the transistor. That is the reason why this base emitter voltage and base current behaves like a forward biased diode. So how this particular input characteristic becomes important, and what are the informations you can take it from the input characteristic? Let us see that. So this characteristic resembles to the forward biased diode curve. It is exactly same as the forward biased diode curve. Already I have told you this is a base emitter junction, and because of the forward biasing of this base emitter junction, it looks like a forward biased diode characteristics. Okay, compared to the common base arrangement, here the base current increases less rapidly with VBE. Okay, so in common base arrangement, basically the base current increases very sharply, but here there is a regular increase of the base current with increase of VBE. Okay, therefore, the input resistance which can be calculated from the VI characteristic curve is observed that it is resistance is slightly higher. The input resistance is slightly higher compared to the CB mode. But comparatively, it is very small, but it is slightly higher compared to the CB mode. To calculate the input resistance, we have to take the ratio of change in base emitter voltage to the change in base current at constant Vc. Okay, that is input voltage divided by input current at constant output voltage. So formula for input resistance is input resistance Rn is equal to change in VBE, that is change in input voltage, divided by change in IB, that is change in input current. It is observed that for small change in VBE, there is a large change in IE. Otherwise, delta VB is smaller, whereas the delta IB is greater. So it is a small value divided by a large value. It means the input resistance of the transistor when it is connected in common emitter mode is going to be very small, and it is of the order of few hundred ohms. Okay, comparatively, compared to the common base mode, it is slightly higher, but still it is very small. That is of the order of few hundred ohms. That is the one of the characteristic property of the transistor when it is connected in common emitter mode. Next, we will take up the output characteristics. So basically, output characteristic is the graph between output voltage versus output current at constant input current. So in CE mode, it is the curve between collector current IC versus collector emitter voltage VC at constant base current IB, because the output current is IC, output voltage is VC, and input current is IB. So if we keep the base current constant, suppose you say 5 microampere is the base current, then we have to note the variation of collector current for different values of VC. Okay, then we can plot the graph of VC versus IC so that VC is taken along x-axis, IC is taken along y-axis. Okay, so basically the collector current increases up to 1 volt. Beyond that, this collector current remains constant. Okay, because the input current IB will influence the value of IC. So after 1 volt, this IC will purely depend on the value of base current. Okay, if base current is taken to be more, then IC also become more, or saturated value of IC becomes more. But you can note that IB is of the order of microamperes and IC is of the order of 4, sorry, is of the order of milliamperes. Okay, so it is observed that this IC will depend on IB as well as the current amplification factor beta. We'll discuss that later. So here you can observe very large change in VC also gives you very small change in IC. Otherwise, IC becomes almost constant. It will not change much. Okay, even the output voltage VC changes. So using that, we can conclude what will be the expected value of the output resistance of this transistor when it is connected in CE mode. Let us see that. So this is the nature of the output characteristics, and we have observed that the collector current IC varies with VCE up to 1 volt. After 1 volt, the correct current becomes almost constant and it becomes independent of VC. So it becomes almost saturated, it becomes flat. Okay. So this value of VC up to which the collector current changes is called as knee voltage. So this is actually the knee voltage. So this knee voltage depends on IB. Okay. This is the knee voltage here, and the knee voltage is different for different value of IB. So beyond knee voltage, this IC becomes constant. Okay. So above the knee voltage, IC becomes constant. However, a small increase in IC with increase in VC is caused by collector depletion layer, which is getting wider and capturing more carriers before the electron hole combination in the base area. Okay. So here, even though the graph looks flat, but there will be small variation of IC with change in VC, but that is not much variation. So for any value of VC above the knee voltage, the collector current IC will be almost equal to beta into IB, where beta is called as current amplification factor. Okay, so we'll see that what is beta in the next slide. Suppose if you calculate the output resistance, that is the ratio of output voltage divided by output current at constant input current. Okay, that is actually delta VC divided by delta IC. Okay, we can observe here large change in VC can cause a small change in IC. So delta VC is greater and delta IC will be very small. So output resistance is equal to a large value divided by a small value. So that is the reason why the output resistance is going to be very large in case of CE circuit also. In common emitter mode of connection of the transistor also, the output resistance is large, and it is observed that it is of the order of 50 to 100 kilo ohm also. Okay, so that is the value of output resistance that can be obtained from the analysis of the output characteristic curves. Okay. Next, another characteristic is the current amplification factor in CE mode that is usually represented by beta. So in common emitter connection, the input current is IB and output current is IC. Okay. And beta is defined as the ratio of change in output current to the change in input current. So that is ratio of change in collector current to the change in base current, which is called as current amplification factor or CE mode. So mathematically, you can represent beta as delta IC by delta IB, change in collector current divided by change in base current. Okay. So usually this collector current is large and base current is very small. And we have observed that less than 5% of the emitter current can flow through the base, and base current is equal to almost 5% of the emitter current. Okay, because of that, this delta IC is always greater compared to delta IB. That's why beta value is very much greater compared to 1, okay, or very much greater than 1. In practice, the conventional transistors will have the value of beta between 20 to 500. So based on the value of beta, you can choose the transistor for various applications. Okay, so basically this type of connection or CE connection of the transistor is frequently used in uh, the circuit which requires more current gain and voltage gain, because in CE mode both current gain and voltage gain are very much greater than 1. So it can produce current gain, or it can increase the current, and also it can amplify the voltage also. So basically this CE mode is most widely used configuration because of the fact that it can give you a good current gain as well as good voltage gain. Where in CB mode, current gain is always less than 1 and voltage gain is greater than 1. But in CE mode, both current gain and voltage gain are very much greater than 1. So it can produce current gain and voltage gain satisfactorily, and power gain is also observed to be very high, because power gain is given by current gain into voltage gain. Okay, so these are the important characteristics of this CE mode.